Good morning, everybody. I hope that you guys are having a great day. I hope that your weekend went well. So today is the 24th of February, and today is actually going to be kind of a short lecture. And the reason for that, I'm going to go ahead and adjust my share so I'm sharing the right thing. Um, the reason for that is we are talking about sugars. But one thing that I do want to mention and reference is that um, there's a couple of things I need to do to our Canvas page, and I apologize for not doing these quite yet. I need to post the recording, our last lecture meeting recording. I will do that today. I'll post today's recording as well. I also forgot last week's day summary. I'm gonna get that up as well as today's. Um, but what we are going into right now is kind of a time right before spring break where we're going to have, you know, introduction and kind of referencing um, some pretty important biological molecules. So, see, chat. We are talking about sugars. Sorry, I just saw that in the chat. And so today we're going to be talking about sugars and their structure. And then what we are going to talk about next time is kind of the metabolism of sugars and their metabolism. Then after that, we're going to talk about DNA and um, lipids. So the reason that we're talking about these different things is because all of these different components are going to feed into kind of where we're going. Um, we are going to be talking about cancers. And in some cases, there are some cancers where sugars get basically metabolized incorrectly, or their metabolism is sped up or it's altered in some form or fashion. So all of these different things, sugars, their metabolism, DNA, and lipids, are all related to cancers. And so that's kind of the direction that we're headed in. And so I just want you guys to have kind of a firm foundation. And those foundations aren't super deep, but I want you to be able to identify different molecules and kind of understand kind of the makeup of them. So yeah, we're going to be talking about macronutrients. So today's meeting is going to be a little bit short, but the way that I suggest you look at that is, okay, it was short, but the information that's there is pretty darn important, and it's something that, I if I spend 5 minutes on a structure, then you should look at that as, okay, I need to spend 10 minutes on it. Um, so just to like reinforce like being able to identify that structure. Okay, so our first piece of information is really kind of terminology. So whenever we talk about sugars, we're going to be talking about the most basic forms and the most basic or simplest forms. The most basic or simplest form of a sugar is known as a monosaccharide. Okay. So that is, a saccharide is kind of a general term for sugars. Um, Ultimately, there are mono disaccharides, there are tri, there are um, disaccharides. And then there's this kind of catch-all term, or there's two catch-all terms. There's polysaccharides, and then there's oligosaccharides. Typically, whenever somebody is talking about a monosaccharide, they're talking about one of these molecules. Now, one of them is maybe the most familiar one for you and for most people, and that is none other than glucose. Glucose is what our body uses as a major fuel source. And, if you um, know anyone who lives with diabetes, then they have to monitor their blood glucose, how much glucose is in their bloodstream. And they have to be attentive to either, what they eat or if they have to have like an insulin pump or an injection of insulin to help their body manage metabolizing sugar. Another sugar that's pretty common for folks to consume is fructose. Fructose is it's another sugar. And notice about these two molecules right here, or what I want you to notice about those two molecules is they have the exact same formula, but they have different names. Why is that? Well, the reason for that is their atoms. Chris, you're absolutely right. Their atoms are arranged differently, therefore they are isomers of one another. Thank you for that. That's absolutely right, Chris. So these are two isomers of one another. Now, do you think, and just add to the chat a yes or a no, do you think that the cells within your body can detect the differences between glucose and fructose? Yeah, absolutely. All of the cells, I can't see your screen again. Didn't fix. Would you mind real quick stopping? Okay. Um, Here I've stopped my share, but now I'm going back to it to help out one of your classmates. Um, so chat. Okay, I've done that. So that is strange. Um, so these are isomers, and all of the cells within your body can detect the difference between them, and your body's going to metabolize them differently. Now, is there any like, has anyone ever seen the acronym HFCS? It's generally like a sweetener around foods people will talk about or hear about HFCS. And whenever I say it, high fructose corn syrup, complex and simple carbohydrates. Well, Stanley, I'm happy that you asked about that because what we're talking about right now is a monosaccharide. These are our simple carbohydrates. So there's a couple of terms, carbohydrate or carbs, saccharides, monosaccharides, oligosaccharides. These are all terms that kind of are within the same sphere and within the same realm. So glucose is a simple carbohydrate, a simple sugar. It's a monosaccharide. There are others, for instance, and we'll get to it, but just as a little bit of a preview, if you've ever heard of the term glycogen, glycogen is also a polysaccharide. And glycogen is what your body uses to store lots of glucose. Now, what I want you to notice about all of these different molecules that I've got the kind of red barrier around, um, they all have a very similar kind of formula. They are all carbons, hydrogens, and oxygens. Now, the numbers of carbons, hydrogens, and oxygens vary a little bit. They have, let's see, if we've got six carbons, then we're going to have 12 oxygens and six oxygens. Okay. Fructose, 6, 12, 6. Ribose, 5, 10, 5. Galactose, 6, 12, 6. Oh, so if we were to look at glucose, fructose, and galactose, those are also isomers of one another. So we've got multiple different ways that the atoms that make up these can vary a little bit. And Stanley, you're absolutely right. They have a ratio of 1 to 1. Now, this right here, this formula is basically the makeup of a sugar. CX, and then in parentheses, H2O, X. So essentially what that tells you is if you have whenever we talk about sugars, we basically look at the number of carbons. And if a sugar has, let's say, 10 carbons, you can predict the formula of it. You can say, well, a 10 carbon sugar, a sugar with AR, 10 carbons, has a formula of C10, and then that 10 would also go in here, and that 10 gets applied to everything in the parentheses, so that would be H20, O10. So it does have a basic ratio of 1 to 1, but this would be the formula, the complete molecular formula of a sugar with 10 carbons. Now, if it had 50 carbons, well, it would be C50H100O10. All right, so O50, I apologize. Um, so sugars follow that simple pattern. Monosaccharides follow that simple pattern. And for that reason, we can use prefixes. We can say, well, if a sugar has 3 carbons, we'll use a tri, and you could say, well, the suffix that we're going to apply is OSE. So it's a triose. It is a sugar with 3 carbons. Then we've got let's go with heptose. You have, well, 7 carbons. So heptose has a formula of C7, it's a 7, H14, O7. Now that formula you can use to kind of go backwards and forwards. Um, One thing that I want to bring to your attention is, well, does this differ from the prefixes that we used for organic compounds? Yes, it does. Now, another thing is glucose. Let's see. Let's go with hexose. Well, hexose has a formula of C6H12O6. Now, add to the chat response to this is, actually, let me rephrase that. Hexose has a formula of C6H12O6. Is glucose hexose? Yes or no? It's not intended to be a trick question. It's a little bit of a tricky question, but yes or no? Yes. Okay. It's well, I'm looking for is it yes. Okay. So, Stanley, your response of isomer. It's a great point because if I ask the question, is fructose hexose? Yes or no? Okay. Getting yeses again. Well, are glucose and fructose the same thing? It's tricky because we've already established that they're not because they're isomers of one another. So this term hexose, this is a good term for classification. If we see a compound with a formula of C6H12O6, that is an example of a hexose. What that means, and what I want you to take away from this, is there are multiple different hexoses. This is my Oprah moment. Glucose is a hexose, fructose is a hexose, galactose is a hexose. There are multiple isomers of hexose. So glucose, galactose, and fructose are all examples of a hexose. All right. Now, the next thing that I want you to know is when we talk about sugars, there's 2 functional groups that are important. There are aldoses, which aldoses have aldehydes. Ketoses have ketones. Now, to illustrate this point of these different sugars, I want to show you this right here. So these are terms associated with different sugars. If a sugar has three carbons, it's a triose. If a sugar has four carbons, it is a tetrose. If a sugar has five carbons, it is a pentose. And if a sugar has six carbons, it is a hexose. Now, what I'm going to do is I'm going to focus on hexose. Hexose is one carbon, two carbons, three carbons, four carbons, five carbons, and six carbons. That is glucose. It is a hexose. Now, I want to show you another molecule. I'm going to do my best to draw it basically the exact same way. Okay. The bond lengths are a little bit different, but they're intended to be the same thing. Okay. Now, this molecule that I've drawn an X under, answer this question for me. Is this a hexose? It's a hexose. Great. Now, my next question. Is this molecule that I have an X under, is it glucose? No, it's not. Absolutely right. The positioning of my OH, of my alcohol groups, also known as my hydroxides, the positioning of those groups is important for identifying whether a sugar is glucose or if it is not glucose. Now, I'm going to draw one last molecule. This backbone that I have here, well, it's a hexose. This molecule that I've drawn a Y under, is it glucose? No, it's not. Is it this same molecule that I've drawn an X under? No, it's not. So these three molecules, what do they have in common? Well, one thing is that they are hexoses. These are all hexoses. Does everyone follow that? Okay, great. Now, there's another thing that makes them similar or maybe identical to one another, or that they can be grouped together. Let's go on to the next slide and take a look at that. Our common sugars, like I said, are going to be aldoses or ketoses. Here is glucose and fructose. Now, take a look at these, and I'm going to go back to the previous slide. All of the molecules that I have pointed out as all hexoses, are these aldoses or ketoses? Add to the chat. Perfect. These are all aldoses. Because whenever we're looking for an aldose, what we're looking for is basically a carbonyl, oxygen, and a hydrogen. So this group up here is an aldehyde, and an aldehyde on a sugar indicates that it is an aldose. So these are all hexoses. They are all aldoses. Now, what we can do is we can take that term and consolidate them and say that these are all aldohexoses. As aldohexoses, well, that gives you a little bit of information that they are aldoses and they are hexoses. They have 6 carbons and they have an aldehyde. Now, with that information, questions that you should anticipate on your exams will be something like, I'll give you a molecule. Say if I gave you this. So the carbonyl attached hydrogen is what makes it an aldose. Absolutely. So what you want to do whenever you're looking at a molecule is if you see this carbonyl and then you see it going to a hydrogen, that is an aldehyde. So I always kind of look for just this right here. If I see that aldehyde, and then we're talking about sugar, so it's an aldose. Sound good, Chris? Okay, cool. So if I gave you this molecule right here, the sorts of questions that you should expect are aldose versus a ketose. That's one question. Next up would be, well, what ose is it? Tri, tet, tetros. Let me erase that A. Pent. So that's kind of the thing that I'm going to ask of you. Can you identify this as an aldose or a ketose? And how would you classify this in terms of the number of carbons that it has? And then, lots of questions that I'm going to ask are going to be comparison. How would you compare these two? Well, they're both aldoses, but one is a triose and one is a tetros. The one sugar, this is the one sugar that I want you to commit to memory is this one right here. And we're going to talk about another variation of this, but I want you to know the structure of glucose, be able to identify it. Okay, so now when we go on, we've got our ketoses and we've got our aldoses. Ketose, the difference is this is known as a ketone where you have a carbonyl oxygen. And then anytime we have a carbon-based chain, we can call that an R group. And then this right here is also an R group. So if we have 2 R groups, but they're different, we call this an R prime, just because we want to indicate those 2 things are different. So a question that I could ask you would be, or that I would like to ask would be something like, which molecule has R and R group, but I'm going to change that. Which sugar? AR, Joel. But no R prime. So which sugar has an R group but no R prime? Well, this whole thing down here, we could indicate that as an R because it's a carbon-based chain. So our answer to this question would be an aldose. Whereas if the question was which sugar has both a R group and a R prime, then your answer would be a ketose. Okay. Now, like I said, I want you to know the structure of glucose. And this next slide, what I want you to see is how many different aldohexoses there are. These are all of the different. Okay. So we use R group. Stanley asked, I don't get the difference between an R and an R prime. Great question. So an R group is the term that's generally used by organic chemists to say let's use The molecule extends from here. If anyone's familiar with, um, if you're writing a list of things, like um, what you would do when you're writing a list would be something like, uh, telling someone to get all the groceries. You would say, oh, get some milk, get some bread, get some, stuff for sandwiches, peanut butter and jelly, lettuce, etc. You'd use etc. when you're just trying to say, we'll get more stuff. There's more stuff that we need. So an R group is essentially like a molecule or a molecular, etc. Does that make sense, Stanley? Okay. And so that's where R group comes from. R prime indicates, well, whatever group I'm indicating here for R, well, this molecule extends in two different directions or has two different kind of continuations, but they're different from one another. So this group that I've highlighted with R prime, in this specific instance, this specific example, this is four carbons. One, two, three, four. Four carbons long. How many carbons long is my R group? My R group up here, this is just one carbon. So my R prime is four carbons, and my R group is one carbon because I'm saying R group extending, and I'm looking at my ketose here from this. Sorry about the confusion there. So from the carbonyl group that I put a star on, I've got an R group that's one carbon long, and then an R prime that's four carbons long. What I'm saying is that R is, is different from R prime. They're just different groups, but they are both kind of like carbon extensions. Does that make sense, Stanley? Did that help? What I was talking about whenever I'm talking about the comparison for R and R prime is I'm just looking at the ketose. Now, if we go over here to the aldose, well, does the aldose have both an R and an R prime? No, it does not. Now, your point here, aldehyde has four carbons on the bottom. It's it's actually one, two, three, four, five carbons. And if I'm referring to this as R group, that's fine. It's like I said, it's just like etc. The R group in one molecule is different from the R group in another molecule. So whenever you use the term R, it's different depending on the molecule that you're talking about. Like I said, it's just like when you use the word etc. If I'm going to say, oh, go get groceries, get bread, sandwich or sandwich meat, etc., that is different from whenever I say, hey, I'm going to Best Buy and I'm going to buy a bunch of electronics, a TV, a computer, etc. Why is the top group not an R on aldose? That's a great question because my R group is in reference to something. So I'm talking about my aldehyde functional group, and I'm saying, oh, well, here's my carbonyl carbon, and then there's an R group attached to it. So what's my focus is my question. Because if I were to draw this, here's another way of looking at it. Whenever I draw an aldose, if if I'm not indicating how many carbons an aldose is, I'm going to draw it like this. How many carbons is it? I don't care. What I care about is that this aldose, well, I know that, or this sugar is an aldose because I have that aldehyde functional group. Now, if I want to talk about ketose, I can write it as this. But I want to indicate that these R groups are different. So I'm going to throw a prime on one of them. And I forgot my oxygen, sorry. Does that make sense? Okay. What I really need you to understand here is to be able to look at the functional group, the aldehyde, or the ketone. And then for this question in particular, well, the aldehyde does not have an R prime. It doesn't have a second kind of continuation because this hydrogen is a part of this is a part of this functional group. So that was just an example sort of question. Now, this is a depiction of all of the different aldoses. So basically it's like showing, yeah, you can make a aldotriose that's 3 carbons. And there's one thing that I want to draw your attention to. That letter D, the capital D that's in front of all of these molecules. Okay, so D-glyceraldehyde. I'm going to tell you that letter D indicates the I'll say direction of one OH, of one specific, I'll say, OH group. Okay. Now, when you look at all of these different structures, how many of these structures have the capital letter D in front of their name? Absolutely. They all have the capital letter D in front of them. Now, what that means is they all have something in common. Let's see, that's 3, 7, all 15 of these molecules have something in common. We all know that they have carbon number 1 is the same. That CHO is another way of just writing this right here. Okay. So do they all have carbon number 1 in common? Yeah. Now, their highest numbered carbon, in this case, it's number 3. In these two, it's number 4. These, it's number 5. And then in the bottom ones, it's number 6. So my next question is, does the highest numbered carbon, so C1, all identical? Does everyone agree with that statement? Okay. Now, if I were to say C3, carbon number 3, and our numbering starts at the top, if I said carbon number 3, they're all identical, would anyone agree with that statement? No, because they're not. Would you agree with, so I'm going to put this as number 1, carbon 1 are all identical. And then my second statement, highest numbered, I'm going to use a hashtag, highest numbered carbons are all identical. Would anyone agree with that second statement? Okay. So when we're looking at these, so carbon number one and our highest numbered carbons, they're identical. So I'm going to cross those out. I'm going to cross them out on every single one of these molecules. Now, with that said, I mentioned that the capital D indicates the direction or the positioning, the orientation, we'll say, of one hydroxide or one OH group on all of these molecules as identical. I've eliminated carbon number one because those are identical. And I've eliminated carbon, the highest numbered carbon, because those are all identical. Now take a minute and look through all of these structures. Look at the aldotrioses, the aldotetroses, aldopentoses, and aldohexoses. Do you notice something common or identical of all of these structures for the positioning of an OH group? And this is kind of a tricky question. Okay, we got C2. Well, we know they're all aldoses because that's carbon number one. Now, Chris, you mentioned C2. Okay, if we look at carbon number two in an aldotriose, would you agree with me that in C2, OH is on the right? Would you agree with that statement? Okay, good. Now let's look at our aldotetroses. C2, OH is on the right. Would you agree with that statement? We've got two aldotetroses. No. Okay. Now I like where you're going with this though. So if we look at, our aldotetroses, carbon number two, those are different. So if we were to adjust this, what would we say? Not C2 has the OH on the right, but instead, what do you think, Chris? Or anyone else? In both of our aldotetroses, would you agree with me that C3? Okay, okay. So odd numbered carbon chains have it on the right. Well, I like where you're thinking about that. I like your thought process and development here. C2 is on the right in our aldotriose. C3 has hydroxide or the OH on the right there in our aldotetroses. Then if we look at our aldopentoses, C4 on all of our aldopentoses, C4 OH is on the right. And then our last one, our aldohexoses, this has C5 OH is on the right. Would anyone agree with these statements and the corresponding trioses, tetroses, pentoses, and hexoses? Okay, great. Now, it's kind of complicated to be like, oh, well, if you add this, then that, and that. What instead we can do is we can say that D has, or D sugars has OH on the right, on the second highest numbered carbons. Does anyone agree with that statement? And just to provide a little bit more context, okay, our hexoses have 6 carbons. Carbon number 5 has the hydroxide, or the OH on the right. Carbon number 4, well, that's a pentose. Okay, so carbon number 4 on a 5-carbon sugar. Carbon 4 is our second highest numbered carbon. Carbon 3, well, when we're talking about a 4-carbon sugar, carbon 3 is our second highest numbered carbon. Now, keeping in mind, how do we do our numbering? Well, our numbering starts with our aldehyde functional group. So 1, 2, 3. So now, applying this rule right here, if you have a D-octose or D-aldo octose, my first question for you is, how many carbons does an octose have? 8. Okay. Is this an aldehyde or an aldose? Yeah. Now, my last question is, which carbon number can we definitively and conclusively say has an OH on the right-hand side in this D-aldo octose? Carbon number 7. And what I'm getting at is with this name, D-aldo octose, here's what you would be able to, put money on as I know I can draw this and I can draw it with confidence. 1, 2, 3, 4, 5, 6. Oh man, I didn't give myself a lot of space. Okay, so that's 3, 6, 7. Didn't give myself enough space. There we go. Okay, 8. Carbon number 8 is going to look like this, CH2OH, because the last carbon on all these looks the exact same. Carbon number 1 at the top, carbonyl oxygen and a hydrogen. And from this name, octose, oct, we've got 8. Aldo, we've got an aldehyde functional group at the top. And then this letter D tells us carbon number 7 is a hydroxide group or an OH on the right-hand side of our molecule. Do we know anything about the positioning of the OH groups on any of these carbons from that name and that name alone? No, we don't. We have no idea about where those OH groups are. Some are going to be on the right, some are going to be on the left. For this point, we don't care. All that we know is the information that we can draw and put down. D aldo octose, we're good to go there. Now, that is the sort of question that I'll ask you. If I gave you, hey, which one of these can I could give you a structure, or I could ask you something like, from the name D-aldo octose, what can you draw? Or what could you put together? This would be the correct answer, because you can't say anything about, oh, well, carbon number 3 has a hydroxide group on this side, and carbon number 4 has a hydroxide group on this side, because you don't know that. You only know that when you have these specific names. And when it comes to naming, which sugar do I want you to know the structure of? This one right here, glucose. I think what's helpful when it comes to glucose and knowing the structure of glucose, know a couple of things. Well, what I'm asking you to know is the structure of D-glucose. D-glucose is an aldohexose. So that gives you that name aldohexose, that basically gives you what to draw for carbons number 1, 5, and 6. So which carbons, if you know how to draw carbons 1, 5, and 6, which carbons do you need to remember? 2, 3, and 4. The way that I've remembered to draw glucose is I think about, okay, it's a D-aldohexose. So 2, 3, and 4, the way that I remember glucose is where do I put my hydroxide groups? I put it on the right, left, right. So I've known the structure of glucose for like 20 years. And so when somebody says glucose, you know what happens in my brain? It goes right, left, right. And I'm done. That's how I draw glucose. I just remember it's like muscle memory. I've said it so many times. All that I care about is the positioning of carbons 2, 3, and 4, because with the name D-aldohexose, I know where to put my other groups. So we spent a good chunk of time on this to come up with this definition in the lower left-hand corner and to be able to use a name like D-aldooctose and get some information from it. Now, with that in mind, here's another way that you can depict, or here are the ketoses. There's fewer ketoses, and there's not any structures that I want you to commit to memory or anything like that. Now, what's more common when it comes to glucose is glucose more than likely is going to be depicted as a cyclic molecule. And so these two are the ringed forms of glucose. The same sort of operation, and I want to number your carbons 1, 2, 3, 4, 5, 6. When I drew glucose, and I'm going to go ahead and draw it right here, CH2OH. Right, left, right. I'll draw the hydrogens in, but with this structure right here and this structure right here, carbon number 2, my hydroxide group is on the right, but then whenever I draw glucose as a ring, it is down. My hydroxide group for carbon number 3 is on the left, and whenever I draw it as a ring, it is up. On the right, down. So right, left, right translates to down, up, down. Does anyone have any questions about that? Okay. Now, with that in mind, this other OH group, whether that is pointing down or up, indicates if we're talking, okay, great question. Okay, so Chris, um, I'm confused as to where the chain starts. Which one is the double bonded oxygen? That's a great question. Where it comes from is this double bonded oxygen right here is actually, it becomes this OH group. So that double bonded oxygen is going to either be pointing down or it's going to be pointing up whenever this linear or this straight form of the molecule is going to it's either going to end up in the up position or the down position. And if it ends up in the down position, that is the alpha form. And then if it's beta, it's going to be up. So up equals left on vertical chain. Yes. I go with RLR equals D U D. Now, for this, so does that help at all? Did my explanation help at all there, Chris? Okay, awesome. And then Stanley, left mirror of right. Um, if you add a little bit more, I can help to explain. Oh, HO versus OH, it really does not matter. Okay. So now what we've got is we've got our beta form of cyclic or ringed glucose or alpha form. These two different sugars are referred to as anomers of one another. That's how they're related to one another. Now, those are all monosaccharides. Here, what we have are examples of disaccharides. Now, what I want you to know, this right here. If I said, hey, or if I ask the question, maltose is a disaccharide of what two monosaccharides? I want you to say glucose and glucose. If I said sucrose is a disaccharide of what two monosaccharides? I would want you to say glucose and fructose. Um, that's the sort of question that I'm going to be asking. Now, to illustrate this point, what these molecules look like. This is an example of a disaccharide. Another question that I could give you is this is a disaccharide and one sugar is glucose. True or false? Just 1 second. Okay. So sucrose, lactose, and maltose. I want you to know what those disaccharides are made up of. Glucose and fructose for sucrose. And there's lots of oses here. So I always just go SGF, LG, and then I'll say like gal or something like that. And then M is MGG. Come up with some like simpler code or mnemonic almost. And G stands for glucose, F stands for fructose, and I'm good to go there. This was the slide that you were referencing, right, Chris? Okay, cool. So now here's an example question. One sugar in this disaccharide is glucose. True or false? Add it to the chat. So to answer this, what you want to do is look at each of these two sugars. Here's one, and then here's the other. Well, glucose, we had RLR or DUD. This is carbon 2, 3, 4. Down, up, down. So this is glucose. I want you to be able to take that straight chain form of glucose and this ring form of glucose and pick it out. When you can pick that out, that's going to be in good shape. That's going to put you in a good position. So if you had a question like this, true or false, true is going to be your answer. Now, this is specifically sucrose, glucose, and fructose. I'm not going to ask you to be able to identify fructose. I want you to be able to identify I want you to know the names of the components of sucrose, and I want you to know the names of the components of maltose and lactose, but I'm not going to ask you the structures of them. I could give you this molecule and say, this is a disaccharide commonly known as what? And then I would expect you to say, oh, well, that's sucrose. Because what I have given you is I've given you the names of the compounds as well. Now, my next, and there's our numbering of each component. The linkage or the bond that brings two sugars together is known as a glycosidic linkage. And this would be the sort of question where I would say, well, what type of or what carbons are bound to one another here? And I would give you the numbers of all of those different carbons. And I do want you to know the bond connecting sugars is a glycosidic linkage. We've had a lot of stuff today, so I'm definitely going to put the day's summary up later. But those are the sorts of things I want you to be able to do. And these technical names, I'm not going to lose sleep over those. So this is another depiction. I kind of got it blurred over. This is another depiction of sucrose. Yes, so there's a lot, but that's because there's a lot about sugars. The quizzes that I'm going to post reflecting sugars, those are going to really capture well what I want you to know about sugars. So again, breathe a sigh of relief that, okay, I don't have to know everything because lots of this stuff is like, you know, biochemistry and organic chemistry that's like super deep. So it can be super deep and there's some stuff I want you guys to know, and I'm going to give a detailed explanation of what that is. Okay, so then here's our other sugars, lactose and maltose, and yeah, lactose and maltose. This is glucose and glucose. This is glucose and galactose. Again, I want you to be able to pick out glucose. If I give you one of these structures, I want you to be able to say like, actually here, another possible example would be which one of these molecules or which one of these components, A or B, is glucose? And I want you to look at that and be like, ooh, it's B, because I know OH goes down, goes up, it goes down. Haha, perfect. That's the sort of question I want you to be able to answer. Okay, that's what I've got for today. I will be posting your quizzes later today. I'll be posting today's summary and today's lecture a little bit later today. I've got office hours starting at 12:30. Stay tuned for those quizzes and the sorts of questions I might ask of you, because I think that will kind of help you be like, okay, this is the information that I need to study. There was a lot there, but this is the stuff I need to focus in on. I'm going to go ahead and stop my share. And then I'm going to stop my recording and I'm going to say, I hope you guys have a wonderful afternoon. I will see you on Wednesday, unless you got office hours.